Ready? Okay, so hello all. I am Sebastin Castro, and today I'm going to share with you a research I have made on Windows persistence. I have named it R&D Hijacking, Maintaining Access on Windows Machines. It's my first time DerbyCon here, so I am quite excited to be here. Thank you. I hope you all enjoy this. So, this is about me. I am an InfoSec nerd. I like exploit development. I am a Windows security enthusiast, not an expert, in fact. My first logo was 25 years ago, and I am a Microsoft Paint artist, as you can see here. I am the current technical research lead at CSL Labs. That is a company that works mainly providing ethical hacking services to organizations working on the financial sector. I have been working on the field as a red teamer, mainly as a pen tester and researcher for about 6 years. Okay, this will be the quick agenda of the talk. I will first expose the attack and how it looks like. I will briefly expose the Windows security architecture related to the login process. Here in the hijacking the RID, I will point out where exactly are the security issues that make this attack possible. And after that, a live demonstration of attacking against a Windows 10 machine I have updated this morning. I hope it will work. And some final conclusions. So let's meet up the RID hijacking attack. So what is this? This is a new post-exploitation vector which is reliable on all Windows OS versions since NT. I have tested it from XP to Windows 10 and Windows Server 2003 to 2012. It creates a stealthy access on the target all by using only OS resources, meaning that no noisy extra files are needed to take advantage of the some integrity issues that I have found that are exploitable with this attack. It is currently reliable on domain joint machines, but not on domain controllers yet. I am working on a similar attack that can be reliable on domain controllers. In short, this attack modifies the RID of an existing account and sets it up to another one. Just the RID, meaning that all the other account properties associated with the user, such as password hash, account status, etc., keep consistent before and after the attack. By hijacking the RID at the exact moment, the privileges will be spoofed. And one cool thing is that no matter what the hijacked account status is, active or no, the hijacker account will retrieve its privileges as on. So remember that only the relative identifier is modified. So an attacker could log on with a specific set of credentials he already owns and get access as another user. Depending on configuration, it will be possible for him to access remotely via RDP, PSXEC, and so on. And besides the privileges stealing, the system will register any operation which has taken place during the hijacker session as done by the spoofed account. And of course, this technique is reboot persistent. So this is how it looks like. In this image, we are running a CMD as the guest built-in account. We can see it, but see in the output of the who am I command. We are still members of the guest local group, but we have writing permissions over the system32 folder, which is pretty cool, I think. So to understand the magic behind this, I will briefly explain how the Windows login process works. The thing is that I am not that pretty good at Paint, but well, I'm terrible. Well, I think that the Windows architecture is pretty similar to the security concepts of some buildings I have been on. So you introduce yourself in front of the guy who is in charge. Then he verifies you if you are registered in their database, and if you are, then he provides you an access card which permits you to get into the zones you are allowed to. So let's assume that this green guy will be the representation of the administrator building account. This red girl will be our main character that will represent an unprivileged account, for example, the guest account. And the bad blue will represent the Windows security, and this ugly building, the Windows OS. Imagine that inside of this building there is an RFID-like control system which is based on the access card the blue guy provides us. To keep it simple, I have drawn 3 floors. I know there are a lot of more privileges, but it's really hard to draw them all. And depending on configuration of the access card, users shall enter inside some specific floors. So this is the Windows security architecture in a more technical way related to the login process. But as you can see, we are ignoring the models related to the AD authentication. That's because the RID hijacking is focused, takes advantage of the way that Windows handles the local user's login process. So we are going to be focused on the LSASS, the MSB10 DLL, and the SAM server DLL. In a nutshell, the logon task is like this. I'm sure many of you have seen this before. So when a new user authenticates through WinLogon, LSASS verifies its credentials and creates an access token to identify his security context to define the security context. And after that, after creating the access token, it will verify this access token against the objects the user is trying to access by using their own access control lists. Okay. Here is the structure of the security identifier. That is the way that Windows has to define, or the way that Windows has to identify security principles, such as users, groups, or computers. The first part in yellow, we can see here that it's the one which differentiates off the machine or domain among others. But the last one, the relative identifier, can be the same across all machines. For example, in every Windows machine, as you may know, the 500 relative identifier is associated with the administrator built-in account. So keep in mind that every user account, local user account, built-in or not, has its own RID. So let's suppose that the administrator wants to log on. So he provides its username and password to WinLogon. To do that, Windows needs to initialize some tasks and connections between processes. Right after, WinLogon calls Logon UI to grab the credentials by using credential providers. And with this information, WinLogon will create an unique Logon SID to identify this logon attempt. And now Windows retrieves the handle for an authentication package, which are used to verify the authentication policies of a logon attempt. Remember that we are focusing on the MSB10 DLL and an authentication package. So WinLogon sends to the authentication package the username password combination with the created logon SID, and then this critical step, the MSB1 sends the user password combination to the SAM server, which retrieves the related security information, including the user security identity. And now, to sum it up, the MSB10 checks the information retrieved. If it is okay, generates another identifier called LUIT for the current session, and sends back the logon information to the LSASS, including this new identifier. All this data will be used by the security reference monitor to define the security context of the user. So we will see that in short. Now that everything is okay, the Windows Security Subsystem proceeds to create the access token for the recently authenticated user. So the access token is used to define the security context of a process. This object is created by the security reference monitor for every user session. It's important to know that every child process inherits a token copy of their creator's one, meaning that every process within a user session will be executed with the same access token. So continuing with the authorization task, LSASS receives the logon information from MSB10 and checks up its own database to determine the user's allowed access. This check is done by using the security identifier of the user. Right after, LSASS adds to the initial access token the related groups, SIDs, and privileges which are associated with this user. And finally, the primary access token is created. Later, WinLogon will call user inits and stuff to initialize everything, but we're not concerned about it. Then LSASS provides the access token to the user session, allowing him to access. Now he can get into the VIP zone. Okay? Yeah, cool. So, now that we went through the Windows standard logon process, let's take a look at the thing we're interested in. Where in the process are something exploitable? So, how is the user identified by the system after being successfully authenticated? It is identified by its associated security identifier, which is unique within the host. How does the system associate a username with his security identifier? With black magic, of course. This is one of the things I have analyzed and versed and debugged to find the security issue. So let me show how this works. So do you remember this part of the process? Here is the exact moment when a username is translated to his associated SID for the very first time. And then some important data is obtained from the SAM. So how is the username associated with the SID and what security information is retrieved? The SAM server now has to translate from username to SID. He goes into the SAM database on this specific registry hive and then selects the username. Each of these keys contains a reg binary, as you can notice here, and these registry binaries have an attribute called type. This attribute contained an hexadecimal version of the relative identifier associated with this user. In this case, is 3E9, which is equal to 1001. Now that the SAM server knows the related RID, he looks at this registry place and chooses the one whose name is the same RID with some significant zeros, and then it grabs all the information stored into the reference key. And SAM server sends back all this data to the MSB1 process, and this is the security data that is returned back to the authentication package. After understanding this process, some questions may arise. So, why does the SAM store only the RID? Because every user will have the same SID initial part, but the RID will always be different for each of them. The only thing that varies from user to user is in the same system, is the RID. What information is retrieved from the SAM? Data obtained from the SAM of the registry contains the password hash, the account status, some additional account restrictions, and the pivotal one, a copy of the user's RID. This is the core of the RID hijacking attack. We'll see that in short. So let's exemplify the attack. Let's do the authentication process with the red girl, but now we will omit some parts of the authentication process and explain in more detail the exploitable one. So guess it's just an example, remember. This worked also on standard user accounts. So omit in the beginning, when logon has done his job and sent the logon information to the authentication package MSB1, and now MSB1 sends the user hash combination to the SAM server. Now the SAM server queried the SAM database looking for the associated guest key. It determines that the guest account has the RID 501 or 1 of 5 in hexadecimal base. So SAM server queries again the SAM, but now consulting the 0000001 of 5 key. Now the process retrieves the security data related to the user, including this RID copy I told you is important. After that, SAM server sends this information back to the MSB1 authentication package, and this guy does his job. So this could lead to two possible scenarios. The first one is that the hacker girl will not authenticate because on every Windows machine, by default, the guest account is disabled, leading to an access denied. Then is the second one. So suppose that for some reason the guest account is enabled, she receives her access token, and then, well, she doesn't get kicked out, but has access only to the guest floor. So how could we improve this situation? It's a mystery for us right now to understand why there's a copy of the RID inside a key with the same name, but what would happen if we modify it? Well, I have found that this RID copy is the value used by the LSASS and Security Reference Monitor to create the primary access token. So the privileges added to the access token are obtained based on this RID. So let's set this RID copy with another RID. In this case, the 500, which belongs to the built-in administrator. So now repeat all the process. MSB sends the user hash to SAM server. SAM server queries the SAM database with the guest username. Then it retrieves the associated RID key, which is 1 of 5. Now it queries again the SAM database with the obtained RID. And now it receives the security data from SAM, including the modified RID copy. This data is sent back to the MSB authentication package. Now that the MSB1 authentication package checks for security restrictions of the user, obtained from the SAM security data. So it compares the restrictions with the data obtained from the SAM. The thing is that MSB1 takes the status of the guest account, but assumes that they are from the administrator, allowing the access even if the administrator account is disabled. As I have told you, the only thing that we are modifying is the RID, not the other security properties. This applies also to the hash. So MSB compares the cached version of the enter password hash, the hash retrieved from the SAM, and profit. Password will be the same. Now that everything is okay, the authentication package retrieves the logon information to the LSASS, and then LSASS communicates with the security reference monitor to create the access token based on this modified RID copy. So all the security properties of the account remain the same except the RID, which is the critical one. Modifying the RID at the exact place is equal to acquiring the privileges of a spoofed account and doing everything you want. In this case, the guest account receives her access token, and she can do anything inside the system on behalf of the administrator. So these are the security issues. The first one is that the SAM server does not check if the RID associated with the user is consistent to this particular RID copy. The second one is that the LSASS does not corroborate the relative identifier with the username right before creating the primary access token. The third one is that the LSASS never looks for RID inconsistencies during the user session. So the funny part, the demonstration. So let me see. This will be our victim machine. As you can see, I have updated early this morning. Yeah. Okay, and here are the latest patches. Here are the local users of the victim, the administrator one, the guest one, and a standard user account called unprivileged. We can see that the administrator account is not active. We can see that the administrator account is active for our demo purposes. Okay. And this is the standard account we're planning to use also. This is active, and okay. So let's lock down. And let's try to interactively authenticate with the guest account. I have set a password before. We can see here that it is not possible for us to interactively log on as the guest account. So I have developed a Metasploit model, which is available on the latest official version of Metasploit. You can see it on, you can find it on Windows Managed Already Hijack. Post Windows Managed Already Hijack. This is the model. These are some of the properties. We'll see that in short. This is the IP address of the attacker machine. And we will try to do a PSXX against the victim and by using the guest credentials. So if we try it, it is not successful by now. We can try it also with the unprivileged account. Okay, it does not work. And let's see the model. So this requires a interpreter session to modify the specific registry binary that contains the RID copy. So the get system will try to acquire the required privileges to modify this particular binary. The guest account boolean will define if we are going to use as the hijacker account, if we are planning to use the guest account as the hijacker one, sorry. If we want to change the password of a hijacker account, we will set it in the field password. And in the field RID, we will set the relative identifier we're planning to set to. And the session or interpreter session. So if we're in exploit, we can see here that we have modified from the guest account default RID, which is 501, to the 500. So if we try to authenticate again with the guest account interactively, let's see. Okay, by now it's possible, but let's see what happens if we try to do that with the PSXX version of the packet. Cool, we'll go to shell. And by default, in packet version, the PSX version of InPacket will try to acquire the most important privilege, with our system account. So let's wait here. Well, the thing is that we are impersonating the administrator built-in account. We can see here that it is disabled. The guest account is enabled. We are authenticating with the guest credentials, but we are generating our access token based on the administrator already. So let's check this. Can you see this? Okay, cool. Now we are the guest account, but our SAD or access token is generated with the 500 access token. Okay, so if we run something like who am I, and we try to write inside of a protected folder. Okay. Okay, it will be possible for us to write on protected folders by using the guest credentials. And no triggering, and by no triggering any alert on the victim. You can see here that it is also the user is disabled by default. Okay, but we are impersonated administrator. So in every log, every log that register any operation that has taken place during this session will be registered as done by the administrator, but we are logging with the guest credentials. This is also, I forgot to do that. I'm running out of time, but it is possible to do this also with the standard user accounts. And some final conclusions. So by now, as you have seen, this is the latest Win 10 version. There is no existing patch to protect Windows from this attack. The only way to defend a machine against this is by detection. I have tested this with many antivirus, but it is not detected. I mean, the only thing that can be detected is the Meterpreter executable, but this can be done also by using only OS resources. The thing is that this is more complicated to detect on big Windows domains, since a simple workstation can be used as an open door to pivot inside the network. I am not currently aware about any malware that uses this kind of persistence. I mean, as you see, this is a quite simple technique and it's pretty easy to apply. I hope you will enjoy this technique as much as I do. And thank you for coming. That's it.